It's my great pleasure to introduce Margarita Davydova as today's two-term speaker. Margarita is a graduate student at MIT working with the and despite the early stage in her career, she's already a rising star who's contributed many beautiful works in lots of different areas, including more traditional condensed matter topics and recent work on quantum error correction, which
Thank you so much. I'm very honored to be here. And so my today's talk is a sort of thought generalization of the body of work on Floquet codes, which is a recent very hyped topic in quantum mechanics. And it's gonna unravel very quickly. So I would love to discuss with questions, because otherwise it might not be useful for the people here. So I know that you heard something about Floquet codes because someone did a talk here, but I will still probably try to give some introduction of that. And I hope I will be able to motivate that, but please still do my question. Okay, I'd like to start about acknowledging my collaboration, which is my what to look like. I had a lot of fun working with them, and they're very brilliant people because of whom this work was possible. Wow. Because of whom it was possible to do this work. Okay, and they're color coded for a good reason. Okay, so now, and that told me that I can do all the different pictures to come in yellow, but I didn't have a yellow shirt. I think it's what he did. We just had good magic. Okay, so I'd like to start by motivating this, but of course, this is just my take on this. There are probably several different motivations. So when we do quantum error correction, we want to protect logical information. And the convenient way to do error correction is by doing this in two-dimensional layout, for which the paradigmatic example of the code protecting positive information is stored codes. So this is one example of a topic where each token corresponds to one technical stabilizer, either X or Z, and these are commuting stabilizers. And by mapping these stabilizers, you project your errors that can occur in your code into X and Z bases. Then it is possible to correct these errors. They have to have a very specific behavior, and because of which you can match these errors. And if the error rate is below a certain threshold, you should get full tolerance. You should be able to guarantee protection for information. However, it's not so simple. In fact, if you infer the balance of your stabilizers with some probability of error, meaning that you might measure an outcome -1 when it should be +1, two-dimensional layout doesn't work anymore. And you have to keep repeating these measurements periodically, repeat this measurements. Basically, you have to have a classical repetition on top of this of repeated measurements, which is actually shown here. So these are repeated measurements of stabilizers. Okay, so now you have 2+1 dimensional setup where you have repeated measurements of stabilizers, and now again you can match your errors, but now you also match your measurement errors as well. And that also works. Now in 2+1 the theoretical heightened threshold, and then there is another paper that is from non-Clifford that showed this 20 years ago. And I would like to argue that historic was the first trivial example of Floquet code, because we have to repeat things in one time. So Floquet codes have been with us all along. Okay, so however, this is a trivial example of the Floquet codes, and as we see that if we want to deal with these non-equal two-dimensional layouts, we have to repeat measurements. We just can't get away with single shot in 2 dimensions. Of course, there are other types of error correcting codes, but we still can learn lessons from considering this code and understanding why, what happens when we take time explicitly into account. So in reality, our original formulation of error correction was time independent, but it shouldn't have been, because there is no fault tolerance if you don't take it into account. So Floquet code sort of fix it. And the auditory code is a trivial example. Floquet codes are a non-trivial example of that. So they give you time-dependent codes, explicitly time-dependent quantum error correction codes, but now they're less trivial. So what's the Floquet code? There does not exist an agreed definition, but you can think of it roughly as follows. It's a measurement protocol instead of a code. It's instead of stationary code now. And these measurements don't have to communicate, so there is something happening from non-terms. And you somehow have to be able to argue that your logical information is conserved, moreover, it's pushed forward in time, and that you have to somehow be able to argue that there should be a threshold. So that was happening. Okay, so and when people think about Floquet, because this is the first code that this is the most famous one. It was invented by Casey in 2021, 2 years ago. And this is a measurement protocol where you measure two body quality operators and link of a given color to three colorable lattice. This is a little bit different version of Casey's protocol than the original paper shows, but this is unitarily equivalent, and this is just a little bit more convenient. So I'm going to be showing this version. I'm going to explain how this version works. But it's ideologically it's exactly the same as the one that John was showing. Okay, so this is the measurement protocol. I will talk about it in more detail later, but this is just the first sentence. Okay, so just to summarize, these codes are still arithmetic codes, but there is no concept of permanent stabilizability anymore. You have to keep into account that each point in time, your state is still described by stabilizer because you're performing measurement and your waveform will stabilize these measurements. Then you somehow have to explain how these measurements allow you to make errors. And finally, unlike regular stabilizer codes, they also possess certain kinds of properties. In this case, we're interested in automorphism property, which we'll also explain later. And that is the possibility of Floquet codes to implement automorphism while evolving logical information is what's actually motivated over. Okay, so then I just wanted to show sort of the areas that people have worked on. This is gonna look overwhelming. But people have in the past 2 years, just because of that one paper on proposals, this is the body of work that the community has output. So they have been producing new examples of codes where the instantaneous code will look differently. Then they have been looking at properties. So you've heard me talk about it recently, talked about topological bulk variants from Donald Hub, but there are a bunch of other works that investigate properties of these codes. And then these codes have been benchmarked with the code. And also, there are two areas, which is boundaries computation with these codes, or actually, sorry. There are two areas, boundaries and quantum computation with these codes, which have been addressed a little bit in the literature, but which are open questions. And I highlighted it for production on this slide. And last time I gave this talk, Craig Dino was in the audience, so I was trying to make fun of him. I'm not sure if it will work here. So he gave a talk on the history of quantum code, but the history is 3 years old. Okay, so now regarding benchmarking, people have run metrics on the left, and these codes are actually better than the Tori code. And Tori code is sort of so far has been fine-tuned, very high performance. Their back-inventory code is a native operation for your architecture are measurements, which is the case for linear optical computing, for example. And they're a little bit suboptimal for regular quantum computing architectures. And people have tried extracting syndromes for this protocol, but this is far above threshold of this. Yeah, so these are the two questions that we address that we sort of to a certain extent solve in our work. But of course, there are other open questions in this area. And I just wanted to say that so far it's the best probably way to do computation. So now I'm going to go over the Hasten's protocol because that's sort of that's needed to do this other concepts. So you start with a three-colorable lattice, and on the three-colorable lattice, the edges can also be three-colored. And then you perform a sequence where you perform two value measurements in all qubits. So here we're performing x-axis measurements on the red edges. Okay, so regardless of which wave function you have started with, as long as it is perfectly handled, it will now also be stabilized by our x-axis operators. So there will be stabilizer group for your wave function. At this point in time, it will consist of these operators. Okay, and next step we measure y operators on green links, and these operators touch the red links. One such operator touches another red operator at one point, so these don't commute. So these are not stabilizers anymore, x-axis operators. That's why y operators are not stabilizers. However, the product of x-axis operators around blue packets still commute with green stabilizers because product of these packets share 2 points with green stabilizers. So now these remain the product, some of the products still remain the stabilizers, so our wave function, but we add the stabilizers. So now our stabilizer group is sort of bigger around. Okay, now the next step we do the same. We measure BZZ operators. Now these don't commute with BZZ because again the blue plaquette shares only a single edge with a blue or single qubit with a blue edge. But if I multiply the red plaquettes of X operators by blue plaquette of X operators by a blue plaquette of Y operators, I'll get a blue plaquette of Z operators, and that's magically commutes with Z operator. Right, so that's how we get the same color as the current round Z plaquettes here. So we have these new updated stabilizers. We have these stabilizers generated from the previous rounds of measurements. And then we have obviously our current measurements. So now our stabilizer group became even larger. And lastly, we sort of performed the cycle trajectory, right? We came back to the same measurements. But by the time we performed the same measurements, we also generated, so this combination of measurements would give you the white stabilizer and green plaquettes. The previous step combination of measurements give you red stabilizers, the red X stabilizers, and lastly we have blue Z stabilizers. So now this is a much larger stabilizer group, and the argument is that if you now continue measuring periodically, you will always have the same rank of stabilizer group. Okay, so now, starting from this round, in fact, you have to prepare the torical measurements and do a cycle between different toricals where the effective lattice will be tensioned in different color. So, so how do we see the toricals? Let's look at our stabilizer group. So the X operators on each edge turn an edge into an effective qubit. So now we can define effective X operator and effective Z operator on each edge. So now we can take these effective degrees of freedom and express our other stabilizers of the wave function in these effective degrees of freedom. And once we do so, on this effective lattice, so now this effective lattice, it chooses red color because with red rounds. So these green stabilizers will become, so now our new degrees of freedom are on the edges of the triangle lattice. Now these green plaquettes will become triangle plaquette stabilizers of the triangle lattice. The red plaquettes will become effective star operators of the effective lattice, and lastly, our blue plaquettes will also become plaquettes in the triangle lattice. But now if you look at this stabilizer group, it is a little bit, so it has Y operators, so it has to be entirely deformed, but in reality, this is just a model where you have qubits on the edges, you have star terms, and then you have plaquette terms. That is the vanilla toric code. And so basically, starting from round 4, you have prepared toric code by measurements. And later on, I will explicitly show and explain why this, why you also conserve logical information. And I will also explain what is the non-trivial automorphism property that is happening. I want to explain why this has a threshold, but you have to look at this really in space-time to understand why it has a threshold. So here I just repeat the properties. Just summarize what I just explained. So basically, after 4 steps, we prepared toric code, and in the original paper that it was called dynamical generation of logical qubits because it started from anything that wasn't stabilized by anything, but actually, and to prepare the wave function that is definitely stabilized by a stabilizing group of the toric code. Then further on, you keep cycling through different validations of the toric code, and and then there are several options like computation for the thresholds and automorphism. Okay, so now I'm ready to talk about our construction in more depth. Does anyone have questions? This is so clear.
Just want to clarify, like basically the protocol here will be measuring the triplet, sorry, not triplet, but like RXX, GYY, and BZZ and everything that in space time.
Yes. Not have to forget about. For each plaquette, there will be only pair of stabilizers going around. So if it's a blue plaquette, its edges are red and blue. So for each plaquette, there will be a pair of measurements that go around. But each qubit will do more than 3 measurements. Okay, so now in order to explain how dynamic automorphism code work, we actually need entire different formulas. So I have to explain the formula first. So this is the formula of anyon optimization. So we are dealing with topological code at every step in time, and topological code representations for anyons. Okay, so in this formulas, measurements can be viewed as condensations of anyons. So this is not the same as broadband condensation, though it's somewhat related to the sample that gives expectation value, but now it gives expectation value to the kinetic operator of the anyon as opposed to its number. So it's condentation specifically of anyons that represent the entire field of topological fields. And then the sequence of measurements is a sequence of condensations in an anyon theory. So we have to have these two pictures, measurements and condensations in mind in order to understand what's going on. So another thing that we need, oh sorry, again I forgot to do something from the previous topic here. In previous talk there was a talk about anyon condensation prefacing my talk. Okay, so for this we also need to introduce the parent model. So the parent model is the model within which we use in order to express everything we're doing. Because if we don't have this framework, we just won't have the right formula. Okay, so the model is called parent model, and for the Hastings-Hahn code, the parent model is the color code that is unitarily equivalent to 2 copies of the Tory code. So this is a model that is technical to copies of the Tory code. This model has qubits in the vertices, and its stabilizers are Floquet X and Floquet Z operators for the Floquets of each color. Now, we have the same number of recitations, so 2 copies of the Tory code, but there is a very convenient labeling of anyons that can be arranged into a magic square. And here I'm putting only anyons that are bosons in the magic square, and I'm not putting an identity like a trivial boson here. So these bosons are labeled in a way that, for example, our X boson corresponds to an excitation that is created by X string along red edges, and it will always violate the Z Floquet stabilizer at the ends of the string. So basically, the bosons are labeled by the kinds of strings that transport create these bosons. So anyons are labeled by the strings.
So you have qubits on both sides.
Yes, yes.
And the color range of what are your stabilizers, the X and Z?
Yes.
So different colors, but they all.
Yeah. On each color, you will have X and you have Z.
Okay.
Yes, it's two stabilizers for each Floquet.
And then when you do RX, you say you go along red edges.
Yes, so what we have XX. That is stabilized Z operator here and Z operator here, which in other language is an anyon here and one end point of the string and one anyon here at the end point of the string. We will call this anyon RX.
So the edges are labeled by the plaquettes that they connect, the color of the plaquettes.
Yes, okay, yes. And then on the right, for convenience, we also show the decomposition of these anyons in the anyons of 2 Tory codes that make products. So, for example, Rx could be thought of as M anyon of the second copy of the Tory code, and so on. So this is like a direct product of the Tory codes on the right, but this is equivalent to this property. And so something got ruined here. Sorry, it's really bad. Okay. So yeah, so here I wanted to explain what. Okay, so one more thing that I wanted to say is that this magic square is arranged in this way because any 3 bosons in the same row, they add up to identity, so they fuse together, and any 3 bosons in the column fuse together to an entity. But if I consider a boson here, it's great material, meaning anti-commutes, the string anti-commutes, with the bosons that are not in the same row or column. So then what's happening is that what does condensation do? So condensation kills one of the Tory code and it leaves the other one. For example, so here I wanted to explain, but I will go back to the previous slide because for some reason the colors flood here. So for example, I can start with the stabilizer group of the color code, which means that I also have an anyon theory of the color code, and I can measure RXX operators, which means I'm condensing RX bosons. Okay, so but now I need to explain what happens to the theory once I do it. In fact, what happens is that the stabilizer group that you will be left with are RXX operators that we just measured, and all the plaquettes that conduce with RXX. And then if you will look at that stabilizer group, that's identical to the stabilizer group that I showed you a few slides ago. So that will be a stabilizer group of the effective Tory code on the red splatters. Okay, so that's like a way to go down from the parent model down to a single Tory code. So, but how do I understand in the language of condensations? It means that I have now a zero expectation value for our X operator or our X bosons. So now they're identified with that. So now, since Ry and Rz fuse together to give our X, because our X and our X is identity, then our I and Rz differ by vacuum, so they have to be equivalent. So now these two bosons become an equivalent boson. And if you look at the right table, we understand it, right? We condense an M anyon, one of the toricodes, with trivialize, we kill the one, that's toricode, right? Then here we have EM and E1. But EM and E1 is just E in the first layer, and on the first layer survives the connection with the second layer, right? So that's a free particle love. So these both bosons now are a simple particle, and these both bosons in the same row are also a simple particle. So these are E and M anyons of the leftover toricodes. So that's one. It's just a copy, right? If you look at the right hand side, you just kill one of the copy of in the second product, right? You left with one another. What happens to the rest of the bosons? These break non-trivially with the condensed bosons. So these have to be confined. These don't exist in the new theory anymore. And this is sort of what I was trying to show here. I was trying to cross out the bosons that don't exist anymore and circle the bosons that are identified. And here I'm just repeating the protocol. So it's RxX, this is the RxX protocol of the honeycomb code, but now expressed in terms of the parent model. And I want to explain how, looking at this chart, you should be able to understand why the logical information survives. And the reason is the following. So the anyon strings taken around the trivial loops of the torus, give you the logical operators. Now, if every anyon string that is not trivial, if any anyon string can be taken from one round to another, it means that any logical operator can be taken from one round to another. So if we have a shared logical operator between one round and another, logical information survives from round to round. This is surprisingly not obvious with this protocol. If you're just read pieces of paper, it will take you time to understand this. So how is it understood? So in this language, it's easier to understand actually. So you just need to make sure that you have a shared logical operator, shared anyon string between the two rounds. For example, let me just fix one anyon string. So this is effective E on the right, and this is effective M on the left. And let me convince you that if I just follow this effective E, so for example, this RZ logical operator, that will survive throughout all the rounds. So first of all, I noticed that RZ and RY are equivalent. So we have two different strings, but they're equivalent if our X is measured.
Now you're visualizing RZ as a string that is
Yes.
on all the RZ.
Yes,
that
exactly.
goes around.
Yes, exactly. So if I have a RZ string and I multiply it by my XX measurements, then I have our Y string, right? So that's why these are equivalent. So RZ and our Y strings are the same thing. But then our Y string, if you look at this round and next round, that string is present in both rounds, unlike our Z string. So if I just kept looking at our Z string, I would have concluded that there is no shared logical E between the two rounds, but there is. Okay, so now I do this with RY. RY actually would be killed in the next round, but if I first update it, we call this update. So we multiply by magnitudes of the current round or by condensed boson of the current round, we'll get BY. And BY is shared between this round and next round. Okay, then I update BY and I get in blue round, I update BY, I get BX. And BX is shared between this and next round. But something really weird has happened. We started from RX story code. We ended up in the same model, but we went from E to M by following the same logical operator. So whatever logical operator was contained in our Z operator, it went to our X operator upon performing the full cycle. That's really weird. That's considered to be a non-trivial property. And this property is called EM automorphism. So there exists symmetry already in story codes under exchange of X and Z logical strings. And performing the round of measurements here implemented symmetry of the toric code. So it brings it back to the same code that implements an trivial logical operation. Okay, so if we just look at one string on the torus of like the X string of the toric code and we compare it to like, and we see that it exchanges with this string along the same direction on the torus, these in fact belong to a different logical qubits. So it's almost like automorphism. So that's a logical gate. Okay, so this sure.
So usually if I just have one copy of the toric code, I can add fields or something, and then this will not release the toric code. here you're condensing both on measurement
Mhm.
and you're leaving the topologically ordered phase in one copy, staying in the topologically ordered phase in the other copy.
That's right.
And by cycling through these measurements, you're doing an automorphism, which is based on a symmetry that's present in just one copy. Because the EM duality is present even in just one copy of the photo.
That's true, yeah.
But you someone need the second copy.
In order
In
to
order-
bring it over through the second copy to a different one from the first copy. That's right, yes.
And you couldn't do it without that second copy.
You couldn't. There, yeah, we were trying to see if we can get rid of the second one. Yeah, that's why the parent code is important. Without parent code, you just don't have a single copy of it. Yeah. Okay, so this is logical gate, but this is a boring logical gate, and topological doesn't have many logical gates like this. So could we come up with more codes such that I can give you like one measurement sequence that go back to itself and gives you one gate, but not a logical measurement sequence that gives you another gate, and this way gets a lot of gates? The answer is yes. These are the codes we propose in our paper. So the idea behind like a general concept of dynamic automorphism code is the following. So we choose a different parent model now that is not a single color code. Then we learn how to condense it into a different codes. Now, if these codes are isomorphic, we could be able to go between them without losing logical information. And that's how we create this graph. We have vertices, we have codes of the vertices, and we have edges for them. We can perform a transition by measurement in these two in the language of parent model. And then it turns out that whenever I make a cycle, the cycle should be labeled by an automorphism. Either come to the same model and the same logical state, or I come to the same model but different logical states. Then I can label each cycle depending on which logical, if I change logical state and how I change logical state, and this means that each cycle is labeled by automorphism. Just to clarify, here we mean automorphism of the topological order, because we really only talk about topological codes are in this language. So these are automorphisms of the topological order, which happen to coincide with gates, with logical gates. Okay, and then if we could consider some closed path, or it has to be closed for gates, but then another path can be added to it after that and the other, and that would be my measurement. The codes. But it's still a question whether it could be a fraction or not. We have to look at it in space-time interval data. And that's the dynamic automorphism code concept. So now to be more concrete, let's go back and look at the honeycomb, summarize honeycomb code with this perspective. Okay, so this is the set of possible condensations. Each possible condensation is shown with the coordinates. But all possible condensation also corresponds to a different kind of torical to get this condensation from the color codes. So each vertex is, you can look at each vertex as either a different condensation or a different target code. Okay, so an edge of this graph is only if I can start from this theory, then perform a measurement. In this case, it will be RZ measurements. And I measure RZZ and I get to this theory. If it's allowed, if I will not lose logical information while doing so, I draw an edge. So each allowed condition will correspond to an edge in this graph. Now, lastly, it turns out that once I construct the graph for this color code, it will turn out to be a torus. And now we can look at half of the graph and label them by automorphism. And some miracle happens. Okay, so if we consider non-trivial cycles on the graph, so for example, these suborbital will be Rx, dy dt, as I showed. That will be the trivial cycle of the torus, that is condensation graph. That will correspond to EM automorphism, which I will describe. Okay, next, if I consider a contractible cycle, it always will not be labeled, but it will be the trivial automorphism. You will actually go to the same logical states. And finally, if you can also have this non-trivial cycle where you wind around both non-contractible loops, but they cancel each other. So you again get a trivial automorphism, and that's actually the first code that we came up with as a follow-up work to this is our. So basically, this is the perspective of dynamic automorphism codes applied to the family of honeycomb codes. So these are all codes that are like honeycomb code, and we just characterize them as if they were dynamic automorphism.
And this is the course because once you go to the sequence operation, we do come back here.
Yes, exactly. Yeah.
And how should I think of the verbal sequence? Like I understand the operation you're doing, but what is it in terms of code?
Oh, it's that like, remember I was writing Tory code and then an argument?
Mhm.
So this would be Tory code
Oh,
of an
okay.
argument, and then X would correspond to what is the edge term that you added to that Tory code stabilizer group. And stabilizer group is the one that I showed in the slide about this.
These are all correspond with that extra, with that little.
Yes.
So the different stabilizers.
They're more like color code, all color code stabilizers, where you add this measurement and you turn it into Tory code, and then you can tell what the rest of the stabilizer group is. Okay, so now I'm gonna summarize our results. Okay, but I still put honeycomb code here because it's just like simplicity not over the code. So then it turns out that it's surprisingly simple to generalize it to an actually useful dynamic automorphism code by just doubling everything. So now you can see that the parent that is 2 copies of the color code, and then your child is 2 copies of the Tory code, which is the color code. If you can do this, you can get away with a bi-layer setup because each layer is a separate honeycomb code, right? It's like a layer and layer. And that gives you you will be able to do protocols in each layer separately. And the only one additional measurement that you want to be able to do is the ZZ measurement between the layers, like in the same vertex. So these are vertex ZZ measurements. Okay. And this is capable of we were able to find cycles on the computation graph for this that perform all the automorphisms of the color codes. That's if I want to guess who doesn't know the answer though. How many automorphisms of the color code there are? Okay, think of a number that you think corresponds to a number of automorphisms of the color code. Okay, so this is it. I'm glad you think of this number. Okay, so color code has some automorphisms because these are all allowed permutations of anyons or logical strings that don't change the algebra between them. So they don't change the code, but they permute the logical strings. Okay, so there are 72 of them, surprisingly. And okay, so each of the automorphisms actually performs a logical operation as well. And now we can translate them, like once we specify when we encode logical information in that ground state subspace, and we can transform the ground state subspace, we can now determine which gates that corresponds to, and in fact, we can do full Clifford group in these codes. Okay, so now just to repeat the concept of quantum computation with these codes. So if I have a working dynamic automorphism code, and we want to do quantum computation with it, we can express quantum computation in a sequence of gates where I have some basis for Clifford gates, fixed basis for Clifford gates. So that will give me a sequence of gates, which is U1, U2, U3. That will be an input data into my dynamic automorphism code. Next, I can express each gate. There is a map between gates and automorphisms, right? So I can express each gate as an automorphism. Now I just translate between gates and automorphism. That will be a sequence of automorphism. Each automorphism is a measurement sequence. So right, it's just a small cycle. So now I have a cycle, combine them together. That's one really long cycle that gives you that sequence of automorphism that as a result, it implements between starting point and final point, it will implement desired quantum computation. If it happens to also be quantum merit correction code simultaneously to that, that's a quantum merit correction code that just evolves in time by itself and does the desired quantum computation. So dynamic automorphism codes are the codes. They're just left to their own device. You just define them as a measurement sequence. Left to their own device, they just perform quantum computation themselves. So your logical information doesn't just live in the code, it also undergoes the desired logical quantum computation. Okay, so then we generalize to the dynamic automorphism code to the simplest kind of theories that we can generalize them to. And we also did 3-dimensional codes. So in 3 dimensions, you can play the same game. You have now 3 copies of 3-dimensional color code. You have 3 copies of 3-dimensional Tory code. And you get a non-Clifford gate. To do non-Clifford gates, one caveat is that we do it by 2 dimensions as well. One caveat is that now we need to do Clifford. We need to do before we needed to do polymetrics, right? You can do a non-Clifford gate with polymetrics. So now we actually have to insert a round of Clifford metrics. And we also need to insert a round of error correction because intrinsic details of how quantum merit correction works in the presence of no Clifford gates. But that round of error correction can be absorbed into measurements. So the measurements have to be made adaptive now. So these are not just fixed measurement sequence, it has to adapt itself to the error pattern that you have. But otherwise, it's sort of the same kind of code, it's just a little bit, it has a little bit of details on top of it, but it can do non-Clifford gates. So we have Clifford gates and we have non-Clifford gates. They're in different dimensions, unfortunately. Yeah, sure. No. Yeah, so you people, some of the people probably were on my talk yesterday, so we can go between dimensions. That's something I don't talk about in this talk, but like we can go between dimensions. That's a good thing. Yeah, sure.
Do you mind commenting on the with boundaries comment? Or
Yeah, so I will have it, so I hope we will get to it. I have an interesting slide for this. So without boundaries, I actually have a really good explanation. Without boundaries, they're logical bits of states, but with boundaries, you can turn them into stringlets, like junctions. And so without boundaries, you can actually show that the most you can have is the real Clifford group, or a subgroup of real Clifford group. So you will never get an S-like gate, but you can, because you can't change the X to Y. There's some sort of like parasitic symmetry going on. So if you create like a triangle, which I will explain in more detail later, if you create boundaries in the shape of a triangle, you'll have logical groups with different geometry. And now you can somehow change X and Y and Y and Z, which means you have other margin S gates. And if you have several triangles, you also have Z gates and so on. But now you have full Clifford group. So you somehow needed these boundaries in order to get a complex Clifford group.
and so the number of automorphisms says 72.
Yes.
But the full Clifford group is larger than 72.
Yes. So that's 72 on a single code. So now you have and yeah, actually we'll again address yeah, sure. That's a good question. Yeah. We do address it more carefully. Here it's more like this is just summary before actually going to in-depth or yeah.
So the non-Clifford gate means you can realize non-Clifford gate in straight.
Yes.
So does that mean you can realize the universal quantity?
Well, we can realize universal quantification not in the same code though. So this code doesn't, it has not Clifford gate, it has some Clifford gates actually, but it doesn't have a universal gates in a single code. So we have to be careful about how we switch between codes. And for the specific formalism, we don't have a protocol that we are confident in that will switch. That has to be worked out. But technically, if you work out how to switch, you would have universal quantification.
And this 3 is 3 plus 1, right? So you can't
Yes.
just do 2 plus 1 and get to 3 then.
Well, 2 plus 1, you get 3,
But
yes,
you need 3 plus 1.
Yeah, that's what yesterday said. Yeah, but here 3 plus 1.
Oh, so you can't use yesterday to get this.
Yes, but the difference is that yesterday I had all L, like sense number of rounds, and here you have finite number of rounds. So here, each cycle that each measurement cycle that you have is guaranteed finite number of steps. So here it's finite depth, like finite time on the
So then you probably can do
Yeah, I'm not sure actually, but that's a very natural statement though. Okay, so now I'm gonna explain it in more detail. I think in the interest of time, I will start skipping slides. I don't think they're really important. I've skipped them, it's fine, I think. Okay, so that's something I already said. And I just wanted to explain more about why exactly these additional gates come. Okay, so the gates correspond to, so there's very nice visual way to understand why there are these anyon in the house. They're just symmetries of the anyon table, because anyon table kind of tells you about the rules of the algebra of the anyons, right? And as I said, there are permutation of anyons of any strings that preserve the algebra, right? So if I somehow can use anyons here, and that preserves the algebra, meaning you preserve the property of the magic square. That's a symmetry, that's in algorithm. And if you look at this matrix where you will actually find some two symmetries, and this is actually I think I didn't write out the symmetry group, but it's S3 times Z2. So it's column permutations times row permutations times 1 or 5. But here we kind of like simply have a generator. So one generator reflection, and then you see it's any E in one layer of the code. So that's actually EM automorphism in one layer. But that's clear we can get, because if we just consider one layer, we run the protocol one layer, that's EM automorphism one layer. Then this symmetry generated has 3 symmetry generated. So that is M in exchange to the second layer. But now we also grow the one generator that couples the layers together. And that makes a generator. This generator exchanges the rows. So now if you just look at this, it exchanges M1 with M1. It's sort of like exchanging X1 with X1 X2. But the operator that exchanges X1 with X1 X2 and Z2 with X1 Z2 is the C. Oh, sorry, it's not. Yeah, so that's like there's a C-not like gate going here. So these three generators will actually be the generators that we need in order to generate all the automorphism. So, but we've seen this already. We've seen this being done. So that's sort of like that's already follows from just two layers of tiny code. But this one couples the layer that doesn't follow from that. The way it works is that we have, okay, as I said, we have separate measurements in separate layers, and these separate measurements condenses each copy of the color code in the parent to a separate Tory code in the child. But we also have a special, and then we can work with these separately. So these are two like two tiny codes. But now we can also do a different kind of measurement. We can take two copies of the color code and then we can turn to one effective color code where both layers are coupled and everything is effective. And that's done by effective vertical measurements. In terms of condensation, it's a little bit more complicated and we want to go into that. Okay, so now our measurement. Yeah, that's sorry about it. Okay. So so we can write it as a sequence of condensations, language condensations. We can write it as a sequence of child codes. So we start with effective color code. We actually then perform the next measurement that is separate measurements in each layer. Then it turns it back into products of two independent color codes. Then we perform something like here using steps separately into layers, and then we try to couple the layers back, but vertical measurements into again effective color code. Okay, but this gate actually swaps green and blue colors, which is that raw sheet that I showed in the last slide, which is that C0 gate which we discussed. Okay, so the reason why it happens is because first they went from the color code to 2 copies of the Tory code, and then from 2 copies of the Tory code to the color code. And if you compare these steps, they are identical, except my color in the second layer has changed. So in fact, that is enough. That's kind of gives the intuition for why the automorphism changes colors. Then we unfold the color code into 2 Tory codes, and we have red and blue, and then we fold back green and red and green instead of red and blue. And that's enough to just exchange the corresponding strings. Okay, so now, so these generators, so 2 linear generator and 1 row rotation, were enough to generate the 72 automorphisms. They're all the 72 the color code. And now, that's not all that we need for quantification. And for quantification, we actually need triangles. So this is the most famous example of a triangle with the color code. So this is why I'm showing it here for comparison. This one is frequent in the literature because the smallest one is actually 713 code. This is the smallest color code. It's a very famous code. But actually for our construction, poly kind of with poly boundaries where you have x breaks in the boundary are more convenient. So what these boundaries tell us is what kind of anyon string can terminate in the boundary. And so for example, on Z boundary, I can terminate a Z anyon string. On Y boundary, I can terminate Y kind of anyon string, and on X boundary, I can terminate kind of anyon string, which sort of gives you the logical operators that don't look like strings anymore, that look like functions now. And that's what sort of buys us the ability to do the Clifford group because that allows us to do the Clifford group, the full Clifford group. And that's because we already know the sequence that gives us permutation between green and blue. But colors in our model, all colors are on the same coordinates, which means that if we can do green and blue exchange, we can do exchange of any other 2 colors, which means that we can permute any Pauli string. That gives you all single qubit Clifford operations, in fact, because Clifford unitaries are niches that act in Paulis and give Paulis. Okay, but that's a single logic qubit. Now, with analytical qubits, we need to add a single entanglement gate, and we actually work it out. It's a little bit, it's a little bit contrived. So I kind of like don't show the details here, but we do work out the intermediate between two different triangles. And now if we stack them on top of each other, there is a concept of pancake quantum computing where you have stacked rows and you can just swap logical operators here and there. And that's how you do quantum computation. So here we have triangular stuff and triangular codes, and that's how you could do quantum computation. Okay, and just to explain why this is a nice method of doing quantum computation is because for every logical gate that we present so far, the time is very slow. So the total runtime of the code has to be long because we're still dealing with like two-dimensional codes here. But the amount of weight that is packed in that total runtime can be proportional to the number of steps because each gate takes a finite number of steps. Okay, so that's what the codes look like in reality. They're a little bit messy. And then, yeah, they're actually almost done. So I just wanted to explain the gist of how non-Clifford is applied. So that is something I already showed on the slide in summary, that like we can draw analogy between 2 dimensions, 3 dimensions, so 3 dimensions. And we go from 2 copies of something to 3 copies of something as a rule. Okay, and now I just wanted to explain non-Clifford gate by analogy with how we do green-blue permutation in 2 dimensions. So in 2 dimensions, remember we sort of exchange blue and green at a level of like before and after we have this like same code, right? Another way of thinking about it is that we knew that we want to do a red-green swap. So we unfold our code, we let it evolve a little bit, and then we can come back to the same step. But now we technically just formally apply this operation that we want to realize, green-blue permutation to the last step. So there's like this unitary that we wanted to apply, it just acts on it has been applied to this step. If we assume that this step should have been same step as number 1. So basically what happens here is that we find a protocol with 3 dimensions that does a trivial gate. And the one that does the trivial gate would have round 1 and round 3 would be the same. Now what we do, we actually take round 3 of that trivial protocol and we conjugate the measurements by the gate that you want to obtain. The gate that you want to obtain is a transversal operation of T gate, which is non-Clifford gate. So we basically can get away with considering a trivial automorphism and then conjugating the last step of measurements by a gate that you want to obtain. And then it turns out there's a bunch of deals here, but then it turns out that you folded into one code and then you went to this code, but this code is already from the gates that you want to apply. Then you fold back and you end up having the automorphism that you wanted. Okay, so now I'm ready to conclude. So we introduced this model quantum computation that's very natural for Floquet codes, just modifies the concept of Floquet codes, such that now it's mixed quantum computation. We also analyzed the ability to do error correction. We provided the list code of error correcting. We show how to do all automorphisms, and this is because the codes are automorphism code, right? Then we show how to make this useful for quantum computation by showing a geometry in which you can do Clifford quantum computation that we show the non-Clifford gates, which together would give us universal quantum computation, and then we finally address some other points. And so I think there is a bunch of interesting theoretical questions, like generalizations of this construction and understanding this construction in more like theoretical level, and maybe understanding how. So we sort of see an example of non-trivial logical dynamics in two measurements here, right? So there is some nice sustainable dynamics, sustainable because error correcting, right? So there is some nice sustainable dynamics that does something non-trivial, that has some trivial properties. So it would be interesting to just understand this better from a theory perspective. And of course, there are quantum information related questions like how to actually make it more useful for quantum computation and how to run this up. Right, yeah, I think I'm done. Thank you so much for
I guess the closest most countries are dynamical automorphism type of code, like like say plus the same type, it's like it does also has some kind of dynamic automorphism structure and like plus the three-dimensional, four-dimensional type of plus the code like being used in like measurement based computation. I'm just curious, like you need to comment on it.
Yeah, that's actually a very good question. So there is a paper by Scott that shows an improvement between project output. They show that between measurement based computation and encode. But that's I think the real reason because measurement based computation in a sense is pretty similar to encode, right? So it offers two-dimensional logical code from one step to another, and it's space-time in a sense, right? So in a sense, these are equivalent, but the formalism is very different, and maybe the mechanisms are different. Here you really have patterns very well controlled. So in a sense, it's like it definitely belongs to one new family of types of computation.
Thank you.
First. So what happens if these measurements are a little different from what we expect? Like there's a little deviation from the projector.
So we haven't looked at, so I think as long as you can expand it to a reasonable measurement basis, so there are no topological, like, I don't know, related measurements. This is just fits into some reasonable error model then, right? And that's literally what quantum error correction of this code addresses. And because your space-time codes, the measurement errors are on the same footing as just qubit errors. So you just address them on the same footing actually. So measurement errors are just, you can think of them as the same as errors happening in your qubits. So you have to address them on the same footing, and then when you have realized error correction, that's error correction for the model where you have all kinds of errors.
This sort of approach is the Floquet a necessary shape, or can you achieve something similar with other shapes?
I think it's relevant and code, and I need to color the lattice, and for color the lattice for inches. Yes, that's it.
Thanks.
Did you see? I want to chat like people with some technology said that they will be sorry.
I mean, it's well within the diffusion-based approach that like they go with.
Yeah, it's very.
So you asked, what is the big picture? But from your perspective, what's missing from your understanding?
I feel like what's missing is that we have been too heavily maybe. I think it's all confidence there, right? So it doesn't have to be a logical one. Especially when it's not that ontological, but still they're not even they're busy for that. They just feel like I don't want to be tied so bad with giant theories when I talk about dynamic codes for dynamic logical information reduction. And just like it in general feels like there should be some sort of formalism doing these kind of things, like dynamics of logical information, but in a very stable way. And predictability turns into error correction, right? But it could be more general physical, less than theory. Right. So I'm being very vague, but it's something we just don't know what's out there yet. It's a very new thing. Like I feel like it's even hard to explain to people who are really think about color codes all the time, or like BBC all the time. It takes a few attempts to explain like conceptually what's going on here. So it's really new. Yeah.
Get dumb question. Do you get any links in the error threshold?
So for these codes, we actually are so the thing that we don't have rigorous proof of fault tolerance really.
Yeah.
So we we argue fault tolerance not that rigorous. It's because you have to have this space-time picture, and now it's not periodic, and that's turned into like a little bit of a nightmare for an actual rigorous proof. So we're actually still working like it would be nice to rigorously prove thresholds or numerically simulate it. Another has been used. We're pretty confident it will work, but again, but then your threshold depends on your code. Yeah. And also, like, I mean, again, in fusion-based architecture, the thresholds are usually much higher than like other modes of computation. So it also depends on what your error model is.
Okay, let's thank Margarita.